So today we start second chapter, electrostatic potential and capacitance. Okay, electrostatic potential and capacity. So what is electrostatic potential? And the concept of electrostatic potential is that, so first we discuss uh, what is the potential here. Okay, so there is a two charge system. Okay, previous lecture series of first chapter discussed the electric field, okay, and two charge theory. So here the two charge, suppose there is a positive q1, that is a source charge. Okay, and this q1 that is charge, and this q1 has a electric field. So here we place a q2, that the test charge. Okay, q2 is the test charge. The difference between the distance between two charge is r, and these q2 experience some force. If both are positive, if red color charge is source charge and q2 is the test charge, so test charge experience some force, that is, this force is called electrostatic force or Coulomb's force. I get that force from Coulomb's equation. Okay, now, so these charge a force experience force, so that's why there's some field, and these charge experience and some force, so that's why a field, and these charge placed in the region of field of q1. Okay, and give that suppose the point, that point is point this point p distance. Okay, so there is force. Now suppose say that if a q charge placed here, just drop here from anywhere, or just drop here, and this q charge not stay. Actually the q charge is move, q2 charge is move away from that q1. So there is some force, so that's away, and these away because there is some energy, there is some energy associated these two charge systems. So see that if q1 q2 charge stay here, not stay actually, they just farther away or displaced in that direction due to there is some force, electrostatic force, and the system has the energy. Two charge system, this two charge system, two charge system has some energy, energy, and these energy associated with potential energy. And there is a electric field. So there is a electric field in that direction. If that is a electric field, so there is some potential, electric potential. So there is some electric potential, potential V, the symbol. Okay. So we see that the from electrostatic force F equal to electrostatic force, that is some constant K, some Q1 Q2 by R square, and that electric field E, some K, basically electric field is a K, but that is a test charge. Okay, and these test charge choose a very small, okay, very small magnitude, suppose 0.001 nano coulomb, and that is a q1 is suppose that 10 coulomb. Okay, the 10 coulomb. So these nano coulomb doesn't much effect that change the system, actually is not possible because that is a very small value, the source charge. Okay, that's why we choose that type of test charge. They do not disturbance that total systems. Okay, So Q E equal to K, electric field E equal to K. So remove that electric field is independent of test charge. So that's why Q1 by R square. And the relation between these two, electric field and electrostatic force, so that is F equal to E by Q. So E equal to QF, E equal to QF, and we know that if electric field is a vector field, and electric potential or electrostatic potential is scalar field. Okay. So there is some potential associated with two charge system. Okay. If the potential, there is some energy, is a potential energy. So here terms come from potential energy. And how this term potential energy came from? What is potential energy? From mechanics, we know that the gravitational potential energy. See that some gravitational potential energy, gravitational PE. What is the gravitational PE? There is some height, h, some object here, and then height of the object from that point A, that is h, and at point B height equal to 0 at point B. Okay, so see very carefully the potential energy, and we know that work kinetic energy theorem or work energy theorem actually, we see the change in energy. Okay, the delta U, that is equal to work done, and the change in energy that is associated to work done, that is to the in a delta U, that is energy, that is equal to final energy minus initial energy. So there is some reference configuration. Okay, so there is some reference configuration. If I say the gravitational potential energy, take an example. So reference configuration is when the object at a ground level, that is h equal to 0. That's the reference configuration. So that is a energy delta U. Okay, a reference configuration from if height equal to 0, that is U equal to 0, potential is 0, and that is here U equal to mgh. Suppose the delta U, okay, suppose this is a delta U. If you suppose ball goes gravitational force, due to gravitational force ball goes top to bottom, that is final energy minus initial energy here, and you see the final energy potential energy will be the 0 and initial energy ui, so that is the delta U. So delta U turns into ui, and that is equal to work done. Okay, that is equal to work done, and that work done is a minus, that is of delta U. Clear? Similarly, when you study the electric potential energy, the being the study of the gravitational potential energy is the reference. Okay, there is some reference configuration. Suppose an ball goes against the gravitational force from down to top. So the change in energy, that is delta U, that is equal to final energy. Now final energy at the top, final energy, that is UA, and suppose final energy UA at the height, and that is UB. Here that case of final energy, see that top to bottom, okay, that's the final energy is this bottom line. Okay, that is UB minus UA. Here when ball goes down to up, someone throw ball upward direction, upward, here is actually downward, this considers downward direction, that is upward direction. And see that very carefully. In upward direction, ball goes from D is a final energy minus initial energy. That is equal to final UB. That is equal to 0. And UB that is equal to mgh. That is a delta U. That is equal to W. So delta U that is equal to W. So here we change the energy. Actually, the depending on when the towards the gravitational force or the against the gravitational force. That's important. Okay. So similar that case, when two charge, suppose one charge is here, and if I bring a one charge test charge from here, these test charge, when I just put a test charge from anywhere, I suppose I bring my pocket or bag, taken out from bag, and these Q2 charge placed at that point P, and then I remove my hand, then Q2 charge just move in that direction, actually move in slightly faster than did that direction actually, because these two are the positive charge and Q2 experience that a repulsive force. You experience a repulsive force. If there is a force, so there is some a force here, so associated with the force, so there is some obviously energy. Okay, so that energy is a potential energy. Clear? The answer came from potential energy. Clear? What is come from potential energy? Okay. Now we have done the some concept. Okay, if you interested to write, suppose that it's a note and key point actually. If there is a two charge system, if there is two charge system, and Q2 is the test charge, Q2 is the test charge, and Q1 be the source charge. Q2 be the test charge and Q1 be the source charge. Okay, and Q1 produce electric field. So Q1 produce electric field, and that electric field is a vector field. That is a vector field. Okay, the field is a vector field, and the Q2 being moved away from Q1. So then Q2 move away from Q1 due to the electric potential. Why? Due to, that's the important point, due to electrostatic potential energy. Very important. The electrostatic potential energy. And this energy U associated with the two charge system. Associated with two charge system. Okay. So U obviously energy is a scalar quantity. Okay, basic. So similarly, introduce the similar the potential, electrostatic potential V, also a scalar quantity. Similarly, introduce the another quantity V, electrostatic potential, the scalar quantity. Okay, and that's potential generated by the Q1. And these potential, okay, these potential V generated by Q1 source charge, similar like electric field. Okay, that's the electric field obviously generated by the source charge. Similarly, the electric potential also generated by the charge Q1, source charge. Okay, clear? Now we discuss there is a two important points. Okay, suppose there are two charge systems. Okay, similar case, and there is some important point. If the work done by the field and there is a conservative energy, and we discuss the work by the applied force. So we skip that part actually, not to discuss now, but we discuss some calculation actually. The calculation is that the main important actually. So there is some source charge capital Q, and now you bring a test charge from suppose from R to P region, R to P point, from being a test charge R to P point. Okay, so from R to P point in that direction. Okay. So test charge, suppose point P, that is called suppose a small q, positive small q. You see that if if a release from test charge here, this test charge move in away actually, because there is an electrostatic force, that is FEL. So FEL in that direction, but some person we applied, or someone we applied external force to overcome that electrostatic force. So the overcome that force is in that direction actually. That is, if I say here, suppose these are called if external force applied to overcome this. Okay. Now similar the condition, same concept. The source charge actually being here, capital Q, and bring a test charge from infinite, here is come for R to P, from infinite point to suppose a point P. Okay, and there is a test charge small q, that's point P, and this point P experience some force in that direction, that is electrostatic force, because the test charge is positive and source charge also the positive, and the distance is supposed as r, and suppose we apply the external force in that direction opposite of the electrostatic force. So the electrostatic potential bring a test charge from infinite to finite region, or from finite region to finite region, suppose R to P, from R to P at that point. Okay. In both cases, the capital Q and the source charge and test charge both greater than 0, the positive. Okay. So here is some work done. That's important is the work done. Suppose in that case, work done from being a test charge R to P, that is equal to integration R to P. Okay, R to P. Suppose we apply some external force R to P, suppose in that direction actually. So R to P, F external same direction, F external dot dr. Similar, R to P, we know that F external force, much more external force, apply some external force to overcome the electrostatic force at the same point from Newton's third law. They are in equal and opposite reaction force actually. Okay, so their magnitude are the same but in opposite direction. That is minus F electrostatic force dot dr. Now if I change the integration, so that is P to R. So electrostatic force is P to R direction, that is FEL dot dr, the direction will be changed. Okay, so that's the R actually, R to P and P to R. Okay. Now the same condition apply here. If a work done for bring a test charge from infinite some to finite region, infinite to some finite region at point P, so integration infinite to a finite region at point P, so we apply the external force dot dr. Suppose same condition is here, infinite to P, if electrostatic force dot dr. Now if I change the integration P to infinite, that is F electrostatic dot dr direction. Okay, clear. So one is a force, attractive force. So actually there is not actually attractive force. They are both are in repulsive force. Okay, because both charge is positive. If someone asks, can I take a test charge with a negative actually? Okay, it's possible. That is mathematically all possible. Because if a test charge, so electrostatic force in that direction towards source charge and apply the external force to bring a hold back from that source charge. Okay, so from away from source charge we apply the external force from away from the source charge, otherwise the test charge overlap to the source charge. Okay, that's why the mathematically both are applied possible, but actually we applied in physics here. That's a positive test charge from infinite to finite. So one is a reference and another is a source. Okay, PSI discuss actually. Okay, when you calculate the potential energy, we choose a reference configuration. Okay, we choose always a reference some reference configuration. Okay, now suppose delta U. Now that is the work done. Okay, so here some the work done related to the potential energy, change in potential energy. Know that. So change in potential in both cases is delta U here. Both cases delta U. Suppose P to R, P to R. Okay, suppose we apply the external force here P to R, P to R, that is equal to W of RP. Okay, so RP means that R2P, and that is we know that why R2P means final potential energy minus initial potential energy. Similar to delta U, that is equal to final potential UP. So R tends to turn into infinite to some finite region, W infinite to P. So work done on test charge. This work done is called work done on test charge. Okay, work done on test charge. Okay, work done applied on test charge. Okay, not a source charge. Okay, you see that clearly. All calculation made in test charge, not a source charge. Okay. So we define the electric potential energy. Suppose the definition, electric potential energy definition. The electric potential energy define. We define electric potential energy. Okay, difference of 2 point charges of charges as a work required to be done by the external force, done by the external force is moving charge, moving charge, charge q, the test charge actually be the, these are the test charge, okay, the test charge from any point to the other point, from any point to the other point. The electric field is a arbitrary charge. The electric field, the electric field is arbitrary charge configuration, or the charge configuration. Why is arbitrary? You choose any distance actually. If you choose any distance from infinite to finite, any point position, okay, that's why it is arbitrary. There are some conservative force. These force, these force are conservative force. Why it is conservative force? Very important. Conservative force, because actually if I test suppose that is source charge here, capital Q, that is some distance here, it is charge small q, suppose being a infinite region to finite region, actually the distance r, actually these force, work done force, these are actually the independent of path, okay, path independent. You choose any path, you choose this path or like that path or like that path, you choose any path, okay, independent of path, independent of path. That's why this electrostatic force actually the conservative force. These are the conservative force. Electrostatic force is the conservative force. Actually, there is a path independent. That's why is a conservative force. You see the very integration very carefully. That is a lower limit to upper limit. So there is a two limit actually. So there is a depend only the 2 point actually. In between these 2 points, the path is random choose. Okay. So that's why there is a path independent, which is any path. Okay. So here some calculation, that is conservative force, very important. Okay, these are the very important line. Electrostatic force is the conservative force. Suppose there is source charge capital Q, there is a test charge plus small q. At the point P, calculate the potential, actually work done at point P, where that distance is the R, test charge 2, and that distance with a capital R, okay, so that is the infinite to point P region, okay, so work done infinite to point P, so that is the external force and that is a F electrostatic force. So infinite to point P means that is the region R, actually the region R, the length is R actually. So R region, suppose that is a F external, F external, F external dot dr. Okay. Now it change the integration r to infinite, that is F electrostatic force. You see the very careful, that is to change the limit dot dr. I know that F electrostatic force, that is equal to r to infinite k capital Q small q over r square, the distance r square dr. So k constant, okay, capital Q small q, integration r to infinite dr by r square. So the vector, okay, FL electrostatic force in that direction, obvious displacement vector in same direction. Okay, so that's why that A dot B from vector algebra, that is AB cos 0 degree, cos 0 over 1, that is AB. So that's why skip that part. Okay, vector addition. Suppose we get a k equal to 1 over 4 pi epsilon, that is capital Q times small q, 4 pi epsilon naught. So integration of 1 by r square, that is minus 1 by r, put the limit r tends to infinite, r to infinite. So that is equal to q small q 4 pi epsilon naught. 1 by infinite minus minus plus 1 by capital R. 1 by infinite equal to 0. So skip that part. That is equal to capital Q small q 4 pi epsilon naught R. That is work done infinite to point P region. Clear? How to calculate? So work done. So similarly, that is SI unit. That SI unit is joule. And we know that that is a path independent. Okay, test charge from R to P, from test charge R to P, R to P, or infinite to P. Okay, so it doesn't depend on path independent. Path independent means conservative force. Conservative force. Okay, so electrostatic force, EL force, is a electrostatic force is a conservative force, means path independent actually. Okay, suppose there is some change in energy, that's also related to work done. So change in energy, delta U, that is equal to work done. We discussed previously the delta U, that is equal to W. Here you see that yes. Delta U equal to W, delta U equal to W. Both cases are true. Okay, because the energy is scalar quantity that doesn't depend on plus or minus W. So a change in energy, that is equal to work done. Suppose if some scalar quantity will be added, UP final. Suppose the energy A, suppose just a numeric value A must be added, and that is R to infinite. Okay, final, that is initial. Suppose added these two, we get work done. That is cancel these two, we get UP minus UR, that is equal to W. Similar condition, if I charge from infinite, test charge bring infinite to finite region, similar condition, that is UP plus A, some numeric value, some constant, suppose 1, 2, that's number. Okay, so UR, so not R, that is infinite plus A. So that's cancel these two. That is equal to W. I know the potential energy at infinite, that is equal to 0. So that is UP, that is also equal to W. Okay, and that W, that is also equal to capital Q small q over 4 pi epsilon naught R joule. So U infinite is the reference. Okay, here is the reference point, and here you see that U R with a reference point is the reference point. Okay, so electrostatic potential is associated being a test charge from infinite to finite region, from one point to another point. Okay, that's very important. So what is the potential now? Suppose there is a definition, say the electrostatic potential energy. Next we discuss what is the potential. So definition of electrostatic potential energy. Definition of potential energy. Definition of potential energy. Okay. Of a charge. Of a charge. Q at any point. Q being means a test charge. So this Q is a test charge. Q at any point. At any point in the work done by the external force, by the external force in bring a charge, bring a charge Q from infinite to finite region, from finite to finite region. Clear? You see that the definition and the equation. See the work done. External force bring infinite to finite region. Okay, infinite to finite region. And what is electrostatic potential? Now the important term, electrostatic potential. Static potential V, that is a scalar quantity, that is W infinite to point P or W R to P, okay, by charge Q, that's a test charge Q, that is equal to work done related to the changing potential energy. So U, suppose P from infinite by Q, or same case U P from any other point except than infinite, that is R point, choose by Q, that is test charge, that is separated by these two, U P by Q or U R by Q, that is equal to potential at point P, potential at point not R, at point R. So this work is obviously potential to plus Q, test charge. Okay. So what is the potential? We see the potential, that is equal to W by Q short form, that is U change energy by Q, that is equal to V, the potential. Okay, this is obviously potential to Q, and that is equal to E electric field, that is equal to Q times Q times F, that is the electrostatic force. Okay, so actually electric field is independent of test charge. Similar the electric potential, that's also a independent of test charge. Suppose we put the value of V, that is W equal to 1 over 4 pi epsilon naught capital Q small q by R. Okay, that is a capital small q by R, and that is Q 1 by Q, cancel these two. So potential V, that is equal to Q by 4 pi epsilon naught capital R. Obviously a scalar. So SI unit is W by Q, joule per coulomb, and the another name is volt. Potential SI unit is volt or joules per coulomb. Okay. So work done by external force, here work done by an external force, by an external force, bring a unit test charge, bring a unit test charge, means a positive, okay, positive test charge from infinite to finite region. Okay, so that's the electrostatic potential at point P. So that is Vp, that is Q over 4 pi epsilon naught R volt. Okay, so potential is a scalar field. Okay, and that's the difference you check, that is a V and E. So E, that is equal to Q over 4 pi epsilon naught R square, that is a electrostatic force, that is equal to Newton times Coulomb. Let's say it is Newton Coulomb, and here is get some volt, means joule per Coulomb. So you see the very carefully, that is a potential is inversely proportional to Vp 1 by capital R, and E, that is inversely proportional to 1 over R square. So there is some difference, okay. The one is a vector, other is a scalar. The one is depending inversely proportional 1 by R, that is 1 by R square. Okay, so next class we discuss more about these two difference, what is the electric potential and what is the electric field, and what is the difference between them, and there is some took some graph. Okay, so you choose introduce the potential at point P. This is suppose a parameter. So okay, if a electric field, so there is some one charge produce electric field. So if they produce the electric field, so there is some potential. That potential is the electrostatic potential or electric potential. Okay, and that's the scalar quantity. Clear? So today I end the class here. If I any doubt in that portion, please put in comment section. I will try to give the answer. And next class we discuss the detail or more concept about these two. And okay, thank you.